Hello, I'm Patty Simpson with Simpson Math. In this video, we're going to create a sampling distribution of sample means. And then we're going to use that to discover the central limit theorem. So first, I'm going to look at an applet. This applet, I'm going to put the link for this applet in the comments of my video so that you can go to this online stat book and see this applet yourself. But this is how this applet works. It's just going to help us to discover and to see what a sampling distribution looks like. So here is some population of data. It's got a nice normal shape to it, that bell-shaped curve that we've been studying about. And so maybe this data is something like women's height. And so we've collected a bunch of data and put it on a distribution, and it has this nice normal curve. Over here we can see the mean of that data. Our mean here is 16. It doesn't work as well with nice women's height, but just roll with me. So there's the mean average of our data. The median, we know in a normal distribution, should be the same as our mean. And then the standard deviation of this distribution is 5. So just for documentation purposes, I'm going to write that down here, that our parent distribution, when it is a normal distribution, when we have this normal shape, see it says shape of the parent population is normal. When it's a normal shape, our parent mean is 16. And then our standard deviation is 5. I'm just going to record that here. In a minute, we're going to do something with it. So now here's what I'm going to do. From that data, that population data, I'm going to take a sample of data. I'm just going to take a sample. Right now, let's start with sample size 5. And so in other words, I'm going to take 5 women and I'm going to measure their heights. And it's going to drop down those 5 women's heights down into this second category here. Then, once I have those 5 women's heights, I'm going to add them up and find the mean of those heights. So I'm going to find the mean of my sample data. And that mean, I'm going to drop down into this third little spot to make a whole new distribution of those means. So let me just show you what I mean. So here I have my population of data. I'm going to drop down 5 women's heights. So see, these are those 5 data points, those 5 random women's heights. And then I found the mean of those 5 women's heights. And that mean I plopped down here. I'm going to do that same thing again. From this parent population, all these women's heights, I'm going to pick 5 of them at random. 1, 2, 3, 4, 5. And then I'm going to drop it down, find the mean of those 5, and drop it down into a new distribution. So this is a mean of my sample data. This is a mean of my sample data. Let's do that again. 1, 2, 3, 4, 5. So 5 data points, 5 random women from in there. Drop those 5 heights down, find the mean of it. So I've got a sample mean, a sample mean, a sample mean, and I'm going to create a whole new distribution of those sample means. Let's do it one more time with the animation here. I'm going to animate it again, 1, 2, 3, 4, 5, so that again I find the mean of those 5 data values and drop that mean down here. So I'm creating a new distribution of sample means, of means that I got from the sample. I'm going to do that 10,000 times. Instead of hitting it one at a time though, I'm going to literally do it 10,000 times all at once. So I'm going to hit that 10,000. See, notice so far I've done it 4 times, just individually. Now I'm going to do it 10,000 times. So I have 10,004. little means, sample means in here that I've created a new distribution of those sample means from that original data. Notice that this distribution has its own mean. Its own mean is at 15 and 9500ths. Its median is there at 1600, and its standard deviation is at 2 and 2700ths. I'm going to do it again 100,000 times just so that we've got a lot of data values here in our new distribution of sample means. There, I've done it 100,000 times. So I now have 110,004 different sample means where I've taken 5 women, found their heights, and then found the mean of those heights and dropped it down into this distribution. I'm going to record this data just so we have it later. So here we had a sample size 5. Our parent mean was still 16. Our parent standard deviation was still 5. That didn't change. But I had a sample size of 5 that I was drawing down each time. And when I did, the mean of my sampling, that's what we call this new distribution. We call it a sampling distribution. It's a sampling distribution of means. And the mean of it is 1599. So I'm going to put that 15 and 99 hundredths in there. And then the standard deviation of this sampling distribution is 2 and 25 hundredths. Okay, let's change our sample size. Let's change it and go back to 2. So right here, I'm going to change my sample size to 2. So instead of dropping down 5 women, I'm just going to choose 2 women. So if I do that, 1, 2, and find the mean. 1, 2, and find the mean. 1, 2, and find the mean. I'm going to do that 100,000 times. Ooh, there's a whole new distribution of those sample means. I've created a sampling distribution of sample means. But my sample this time was just sample size 2. Notice it still has that normal shape to it. But when we compare it to what we just did with the 5, hey, my mean of that sampling distribution is at 16. The median is also at 16. But notice the standard deviation of this thing is a little bit bigger than when the standard deviation, when my sample size was 5. Let's see what happens when I make my sample size 10. So in other words, I'm now going to pull 10 women's heights from my original population. Watch it go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to find the mean of those 10. I'm going to create a sampling distribution of those sample means. So here's a sample mean from this sample of 10. I found the mean, so that's a sample mean. I'm going to create a whole distribution of those sample means. So let's do that 100,000 times, where I drop down 10, find the mean. Just for fun, let's do it another 100,000 times. Notice it still has that fairly symmetric shape. It still looks pretty normal. Then let's look at the mean of this new sampling distribution. It too is right there at 1599. I'm going to write it down just for us to look at it again later. And then notice that the standard deviation this time got a little smaller. We're at 1 and 58 hundredths. So our parent mean, though, didn't change, and our standard deviation from that parent distribution didn't change. Let's increase the sample size again. Let's increase it now to 16, and just see what happens when I increase it to 16. Does it change anything as that sample size gets larger? So I'm pulling out 16 women's heights from this parent population. I'm going to find the mean of these 16, and that mean goes there. I'm going to do that over and over and over again so that I create a whole new distribution of means, a whole new sampling distribution of means. Let's do it 100,000 times, maybe even 200,000 times. Notice again that that distribution is still approximately normal. Here, my mean is 16. My standard deviation, though, got even smaller. So it was 1 and 58/100ths. Now we're at 1 and 25/100ths. My parent, though, that mean and that standard deviation did not change. We'll do it one more time with this shape of normal, and then we'll try a different shape from our parent and just see what happens when we do that. So here, let's jump all the way down to 25 now. So in other words, I'm choosing 25 random women from this population distribution. And I'm going to find the mean of that data. I'm going to create a whole new sampling distribution of those sample means. So I'm going to do it 100,000 times, 200,000 times. When I do, here again, I have this nice symmetric shape to my new distribution. My mean right there at 16 still. But my standard deviation again got even smaller. Now it's only 1 is my standard deviation. So that data is getting closer and closer. The means, those sample means, are right in this little area, this tiny little distribution. They're not very spread out at all. And my parent mean and my standard deviation is still there at 5. So when my population was normal, notice that as my sample size increased, the mean of the distribution stayed right about 16. But look at that standard deviation of this sampling distribution. As my sample size increased, that standard deviation got smaller. Let's try it with a different shape and see if it changes anything. So this time, let's make the shape of our parent population skewed. So I'm just going to take this shape, this parent population, and let's make it skewed. So inside this little applet, it has this nice little animation, and we can change it around a little bit just to kind of look at this sampling distribution. And here's a skewed parent population. Notice that this one is skewed to the right. Those values over here on the right would pull our mean to the right, so it's skewed to the right. And let's see what happens when I do the same thing. So maybe this distribution is, I don't know, salaries, where most people make right in this this range. You know, they're right here, but you've got your supervisors, the people who've been there longer, your president, CEO, so they skew that salary distribution to the right. And let's start at our smallest sample size, where we're just choosing 2 employees and looking at their salaries. So I choose randomly 2 employees, and I find the mean of those 2 employees. And I do that over and over and over again. Find the mean of the data. Find the mean of the data. And I'm going to create a new distribution of those means. A sampling distribution of sample means. So I do it 100,000 times. 200,000 times. It's still pretty skewed to the right, isn't it? That distribution looks still skewed to the right. Maybe not as skewed as this one was, but it still looks skewed to the right. Let's record some information just so we can look at it here in a minute. So the parent of our skewed population has a mean of 8 8/100ths. And this parent has a standard deviation of 6 22/100ths. Notice that the mean really is greater than the median. It shows us that it really is skewed to the right there. Let's look at our sampling distribution that we created of sample means. And the mean of that distribution is 8 8/100ths. And the standard deviation there is 4 and 41/100ths. Let's do this with a larger sample size. Let's see if the same thing happens that happens before, where our standard deviation gets smaller. So I'm going to change my sample size to 5 now. And let's again pull 5 salaries, find the mean of those 5 salaries. Let's do that over and over and over again so that we create an entire sampling distribution of those sample means. So if I do 100,000 times, 200,000 times, I have a new sampling distribution of sample means. And if we look at that sampling distribution, my mean is still right there at 8 and 8/100ths. But my standard deviation now is at 2 and 78/100ths. But my parent was still 8 and 8/100ths and 6 and 22/100ths. So notice that when I increased my sample size, it really did get smaller, that standard deviation. Let's also look at the shape of this distribution. Notice that the shape of the distribution is not as skewed right as it was. It's getting more and more symmetric. Let's see if that continues if I make my sample size even larger. So now let's check a sample size of 10. So I'm pulling out 10 employee salaries. I'm going to find the mean of those 10 employees. I'm going to create an entire new sampling distribution of those sample means. I've done that 201 times. And notice in this new distribution, the sampling distribution of sample means, my mean of that sampling distribution is still 8 and 8/100ths. And the standard deviation is at 1 and 97/100ths. It got smaller. And notice the shape of this. My mean and my median are getting really close to one another. So it's looking more and more normal, more and more symmetric. So the parent was still there at 8 and 8/100ths and 6 and 22/100ths. Let's raise the sample size again. So I pull out 16, find the mean. I do that over and over again, create a new sampling distribution, and notice that it's even looking very symmetric. My mean of that new sampling distribution is still 8 and 8/100ths, and the standard deviation now is 1 and 56/100ths. So again, we're just getting smaller and smaller with that standard deviation. In other words, my data is less and less spread out. It's getting closer and closer together. One last time with this skewed data, let's do it with a really large sample size of 25, so that I'm pulling out 25 different employees and their salaries. I'm going to find the mean of that data. I'm going to do that over and over again. So there's my sample mean. I'm going to create a new distribution of those sample means. Do that a couple of 100,000 times. And I now have 8 and 8/100ths, and my standard deviation is 1 and 24/100ths. So notice that the shape of that is again very symmetric. So even though my parent population was really skewed to the right, as I found those sample means and created a new distribution of sample means, this new sampling distribution was approximately normal. It was looking more and more normal the larger my sample size. Cool. And my standard deviation, as my sample size increased, my standard deviation got smaller. Let's do this one more time, where I have the shape of the population, my parent population, is some custom. So I'm going to take this and I'm going to change my parent population to something that's custom. I'm going to draw some really weird distribution. I don't know what it is. I've collected data and it's just really odd looking data where, I don't know, maybe it's, I have no clue. Some weird data where the data is just all over everywhere. That's a weird shape. Now, but I'm going to do the same thing. So here in this custom data, my mean of that distribution is at 17 31/100ths, and my standard deviation is 10 78/100ths. I'm going to take and start with just 2, where I take 2 random pieces of data and I find the mean of that. I'm going to do that 100,000 times. Well, when I do that with that really small distribution, really small sample size, this still looks fairly similar to its parent there. It's got a few more bumps in there, but it's still really, really weird looking data. Even at those, some weird looking data. So now I'm just going to record that sample mean. The mean though is still really close to its parent. And the standard deviation is at 7 63/100ths. I'm going to raise my sample size to 5. So I'm now pulling out 5 of those data values and finding the mean of that. I'm going to do that 100,000 times, 200,000 times, and I'm going to look at this shape. Notice that it doesn't look as much like its parent as before. So as I increase that sample size, the means, this distribution of sample means, looks more and more symmetric, more and more normal. So let me record the information so we can look at it here in a second. So the mean of the distribution is 17 33/100ths, and the standard deviation is 4 82/100ths. Raise that sample size to 10, and we do the same thing where we pull out 10 of those data values, and then we find the sample mean, that mean of that sample. We're going to do that over and over again to create a distribution. And notice that that distribution is looking more symmetric. And the standard deviation is even smaller, so my data is getting closer. Those sample means, this sampling distribution has a smaller standard deviation. A couple more times, I'm going to do that with a sample size of 16. Create a sampling distribution of those sample means. Just write down our data here. So our mean of that new sampling distribution is still 17 31/100ths. And our standard deviation is 2 69/100ths. Parent mean is 17 31, and that didn't change. Then, one last time, let's make a really large, or the sample size of 25. Do that a couple of 100,000 times where I pull out that data, find the sample means. So notice that the mean of this sampling distribution is still the same mean as its parent, but the standard deviation of this sampling distribution has gotten even smaller. So a few things that we've noticed as we've done this. It turns out that no matter what my parent distribution is, when I pull out data, a sample of data, and I find a statistic from that data, in this case my statistic is a mean, I'm finding that sample mean, and I create a new distribution, a sampling distribution of that sample data, this new distribution is, as my sample size gets larger, this becomes more and more symmetric, or it approaches normal. And my mean of the distribution stays right about the same as the parent mean. Notice that the mean of our custom was about the same as the mean of the parent. The sampling distribution mean of our skewed was the same as the mean of the parent, and the mean of our normal was the same as the mean of our parent. But the standard deviation, as my sample size increases, the standard deviation for my sampling distribution decreases. Now I want to look for a minute just to see if we can figure out how this is decreasing, or what the ratio is or what's causing that decrease. We know that the sample size is helping with that decrease, or is causing some of that decrease, because as our sample size increases, we see that the standard deviation decrease. As our sample size increases, our standard deviation decreases. So what we're going to do is we're just going to find the square root of our sample size. So this square root of n, I'm just going to take the square root of this 2 and see what is the square root of 2. So on my little calculator, you can do it on your calculator, I'm just going to find the square root of 2, which is about 1.41. Then I'm going to find the square root of 5. So here I'm going to find the square root of 5 is 2.24. Then the square root of 10, if I do the square root of 10, then that's 3.16. We know the square root of 16 is 4, and we know the square root of 25 is 5. Now those same numbers will be true no matter what the shape of my distribution was, because the square root of these 2, 5, 10, 16, and 25 stay the same no matter what. I'm going to use this information here in just a second. So I'm just going to fill in this little chart to help me see this information. Now, what I'm going to do is I'm going to take my parent standard deviation, and I'm going to divide it by this square root of my sample size, and I'm going to see what happens. So in this case, my parent standard deviation was 5, and I'm going to divide that 5 by this square root of n. So I'm taking 5 and dividing it by this 1.41. And I want to see what that is equal to. You can do this at home too. Just take out your calculator and do 5 divided by 1.41 and see what you get. I got 3.57. I'm going to do that for each one of these. In this case, my parent standard deviation was still 5. I'm going to divide that by the 2.24, and I'm going to see what that is equal to. So the standard deviation of 5, I'm dividing it by the square root of my n, which is the square root of 5, and I just want to see what that's equal to. 5 divided by 2.24, I got 2.23. 5 divided by standard deviation of the parent divided by the square root of 10 is 3.16. So if I do that division, then I get 1, that equals 1.58. I'm going to take 5 divided by the square root of 16, which is 4, and 5 divided by 4 should be 1.25, and then the standard deviation of 5 divided by the square root of 25 is 5, which equals 1. Now, I want you to notice when I did that. When I took the parent standard deviation and I divide that, I take that parent standard deviation and I divide it by the square root of my sample size. Notice this 3.57, this 2.23, this 1.58, 1.25, and this 1 show up really close on this other column. So when I take the parent standard deviation and divide it by the square root of my sample size, I get something really close to, or exactly, the standard deviation of that sampling distribution. Let's see if that works when my population was skewed. Is that going to be true for here as well? Let's test it out. I'm going to take that parent standard deviation of 6.22. I'm going to divide that by the square root of the sample size, in this case the square root of 2, which was 1.41. And when I do that division, 6.22 divided by 1.41, we get 4.41. Hey, that's the same as what our standard deviation of our sampling size was, our sampling distribution was. Let me try it again. 6.22 divided by 1.41. When I divide that, not 1.41 this time, but 2.24, because that's the square root of 5. When I divide that, 6.22 divided by 2.24, sure enough, we get 2.78. Wow, it really does turn out to be that standard deviation of the sampling distribution. We can do that for each one of them. I'll let you do it at home to test it to make sure that it works for all of them. But it should, if I do this division each time, I divide 1.97. I divide the parent standard deviation by the square root of that sample size. I should get the standard deviation of my sampling distribution. So this parent standard deviation divided by the square root of my sample size ends up being the equal to that standard deviation of the sampling distribution. So we have now discovered the central limit theorem. And the central limit theorem tells us these things. It says that when you have a population, no matter what that population of data is, that population distribution, when you pull out a sample from that distribution and you find a statistic from it and create a whole new distribution of those statistics, in this case sample means, when I create a sampling distribution, when my sample size is large enough, it does have to be large enough. So really we say it has to be at least 30. Now we were seeing some symmetric distributions even at smaller sample sizes. But we say that that sample size needs to be at least 30 to make sure that it's a nice normal distribution. So when we pull out a sample size of at least 30 and we find a sample statistic and create a sampling distribution, that sampling distribution will be approximately normal. The mean of that sampling distribution will be approximately the same as its parent, and the standard deviation of that sampling distribution will be the parent standard deviation divided by the square root of the sample size. Math Made Simple is Simpson Math. Thanks for watching.